But the point is that there's this very important special fiber, the degeneration fiber, where my H-bar connection becomes a Higgs field, where the system is no longer a differential equation; it's an algebraic equation, and those are much more those are much easier to study. So in particular, we know about the Eigen decomposition of endomorphisms, and so the same holds true for holomorphic or meromorphic objects. So if I have one of the meromorphic Higgs bundles, then generically and locally, so locally away from branch points, points where the eigenvalues collide, and for generic in generic situations, in terms of the discriminant of my endomorphisms, etc. So once all these genericity assumptions are satisfied, then locally I can always decompose my Higgs bundle into a direct sum of line bundles. So it's a direct sum decomposition, just an eigenspace decomposition, where these eta i's, they're just eigenvalues of my Higgs field. Now, of course, a Higgs field is an endomorphism valued in differential forms. So these are differential forms. The eigenvalues are differential forms, meromorphic differential forms. But basically, you get this nice kind of very simple local picture where you decompose Higgs bundles into something very simple. So somehow the point is that you would want to do the same with connections, but it's a bit more complicated. So the way to access it is what I call WKB filtrations. So a kind of rough punchline of the entire talk is that given a number of genericity conditions to be satisfied, then at least in rank 2, higher rank is it's work in progress, but at least in rank 2, if I have such a meromorphic H-bar connection, then you can show that the vector bundle E, which carries the connection, has a canonical filtration. It's a flat filtration, so the connection sends pieces, the nth piece of the filtration to the nth piece of the filtration. So in other words, you could think that it's like a triangular, upper triangular, has a triangular form in that filtration, and there's also this word piecewise. So by that I mean that my Riemann surface is covered, or rather x minus finitely many points, so a dense open subset of x is covered. It's like tiled with these open sets, cellular, like cell open sets, which may intersect. So it is a covering, and the point is that these open sets, they're kind of canonically defined, and on each of these cells there is a canonical filtration. So this filtration is not a global filtration, but it's also not kind of a local filtration. It really is like a piecewise filtration. For each cell there is a filtration, and these filtrations, So that's the structure you get. You have this canonical piecewise filtration on the bundle, and the most important property about this filtration, from the point of view of the fact that we're studying not just a connection, but a family of connections, this very special family of degenerating connections that limit to a Higgs field, is that this filtration has a very, very strong relation to the eigenspace decomposition of the limiting Higgs bundle. Namely, it's the equation that I wrote here. So you take this filtration, and you can take its associated graded. So that is some kind of direct sum of line bundles with rank 1 meromorphic H-bar connections. And you can consider the limit of that as H-bar goes to 0. And it turns out that is canonically, such a associated graded is canonically the eigenspace decomposition over each cell. Now, so there's like this statement is in a way is very rough because I'm hiding a lot of kind of complicated detail. One of them, really important one detail is that this filtration. So even if you're, even if you start with a system which is in the H bar space is defined on some open disk around H bar equals 0, or hell, even on the entire complex plane, H bar complex plane, then it turns out that generically such filtrations, they only exist in sectors in the H bar plane. They don't they certainly, they're not holomorphic at H bar equal to 0. They exist in sectors. And so so when I write this statement, limit of a bundle, if this thing were well defined and holomorphic at H bar equal to 0, it's easy to understand what I mean by that. But if it's not, then you have to work a little bit. I don't think, maybe at the end I'll say a couple of words, but it's basically just, you just need to be careful about kind of extension of scalars type of functorial argument. But anyway, I just want to make a comment that there is a kind of a very precise algebraic way of making sense of what it means to take a limit of a bundle. Okay, so these filtrations, they have several very, very nice properties that I want to kind of advertise. So one of them is the fact that the filtrations are transverse. So remember I said this is a piecewise filtration, and these pieces, these cells, they do intersect. And so on each of these intersections, you basically have different filtrations associated on the same bundle. And so that you could ask a question: how do these filtrations differ from one another? And the answer is that they generically they are transverse to each other. Which of course in rank 2 just means, in rank 2 a filtration is really just an inclusion of a line bundle. So what that means is that over one such intersection, the two line bundles that I get via this canonical construction, they're genuinely different. They're distinct line bundles. So the important consequence of that is, as usual with transverse filtrations or transverse flags, the best thing to do is to intersect them. And when you intersect transverse filtrations, you split the vector bundle. And so what happens is that over each cell, you have a canonical filtration, and over each double intersection, or each component of each double intersection of these cells, you have canonical splittings, canonical decompositions of my vector bundle. And this this decomposition, it decomposes. Sorry, my pen is refusing to work. This decomposition, it decomposes my vector bundle E of, say, rank 2 into a direct sum of two line bundles with a connection. So this is now a rank 1 connection. And this, of course, has now the property that if that is also an H-bar connection. If I take its limit, then it becomes this Eigen space of the Higgs bundle. So you could say another way of saying it is that basically there's a way to make this more precise. Basically, this connection, this H-bar connection, rank 1 H-bar connection, del I, looks like maybe in a local trivialization as H-bar times D, the de Rham differential, plus the eigenvalue of the Higgs field, plus things of higher order in H-bar. So basically, that's the idea. That's the statement, or that's the picture. Okay, so there's another really important property that these filtrations have, and it's that they play very nicely with another type of extremely important filtration that you get on a meromorphic connection, whether H-bar or not. And that is a filtration at the poles by growth order of solutions. So these things are they don't really have a well-established name. I usually call them Levelt filtration because he was more or less the first one to try to systematically study them. But basically, what happens is if you have a meromorphic connection and you study its space of flat sections near a pole, and you take your flat sections and you start parallel transporting them into the pole, then these flat sections, well, they, because this is a singular point for the equation, they experience various growth behavior. One thing you could do is you could ask which one of them grows faster than another. So it's basically it's almost like taking ratios of sections. If it's a scalar differential equation, then that's literally taking a ratio of two solutions, and you can drag that into a point, and then you will see that it either decreases exponentially to zero or shoots off to infinity. And so by taking these comparisons of your flat sections, it turns out that the vector space of flat sections near a pole, you can filter it by growth rates. So the first step in the filtration would be sections which grow the slowest, or maybe decay the fastest as you go into the pole, and so on. So this WKB filtration, kind of remarkably, I particularly like this property very much. These WKB filtrations, turns out that they're defined on these pieces, on these cells, and these cells are somehow associated with poles of my connection, or more generally, if a pole is of higher order, then it would be associated with the corresponding Stokes sectors as a pole, and so you basically have this WKB filtration on the entire cell, and then in the germ neighborhood of a pole or the Stokes sector, for each fixed value of h bar, you just get an ordinary meromorphic connection, and you can look at the Levelt filtration, and so now you can compare the two, and the upshot is that they're the same. So the WKB filtration literally recovers, or it restricts to the Levelt filtration. So that's kind of really neat. Okay, so I guess a word about why do I call them WKB filtrations in the first place. The reason is that there's a super important special case of this whole business, and that is the case of Schrodinger equations. So just one-dimensional, complex, whatever, stationary Schrodinger equations. So in order to see the connection, you kind of need to geometrize a little bit the situation. So instead of thinking of a second order differential operator in coordinates, I would look at what is called an SL2 opper, SL2 h bar opper. So in this case, what you should look at is you should look at the first jet bundle of a very specific line bundle on my Riemann surface. This very specific line bundle is the anti-canonical line bundle. Actually, sorry, square root. I forgot. Should be square root anti-canonical. So these are, in quantum mechanics, we often say whatever, we integrate half densities or anti-half densities or something like that. So that's why this line bundle appears when we study the Schrodinger equation. That's what allows the Schrodinger equation to kind of keep its Schrodinger equation form as we go from one coordinate patch to another. That's why we are allowed to kind of always remove the first order derivative term. So that's because it's a differential operator on this very specific line bundle, and so I'm just going to promote it to a connection on the first jet bundle. This is just the usual. If you don't know that word, this is just the usual operation where in differential equations, where if I have a differential equation of a higher order, then I just introduce new variables where if it's like if f prime is g, then f double prime is g prime, and so on, and so I transform my scalar differential equation into a system. So that's just it. That's all I'm doing here. That's what it means to take the jet bundle. And then the connection is just the jet prolongation of the second order differential operator. So so this is the usual form for a Schrodinger equation for a Schrodinger operator. Yeah, I may or may not want to let my potential depend on h bar. Usually I do, and maybe in some very bizarre way. Anyway, so the point is, the connection is that now this is a meromorphic h-bar connection, and so I'm claiming that it has this WKB filtration. So how does it relate to some other things that we know from studying the Schrodinger equation? Well, the fact is that the filtration, which is the inclusion of a line bundle, that line bundle, which I call here E1, that is generated by the one jet prolongation of the exact WKB solutions. So that's why I call these filtrations WKB filtrations. They're kind of natural generalizations. In fact, yeah, this is the last point on the slide I want to make, that hopefully this example convinces that the kind of construction of these WKB filtrations is a generalization, a genuine generalization of the WKB analysis from from just second order linear differential scalar differential operators to a slight kind of invariant degeneralization of them, which are these SL2 operas, to general h-bar connection on a on an arbitrary vector bundle on a compact Riemann surface X with arbitrary poles, etc. At least in rank 2, and in rank n, I think I think I have most things in place. There's just a few kind of things that I'm still working out, but the kind of the general the same, more or less the same idea just kind of goes through. You just need to, yeah, it's just a little bit more complicated.
May I
but in rank, yep.
Yes, you are talking about upper. When you have an upper, you have also a filtration, but which is not invariant by the connection. You have transversality. So your WKB filtration should be transversal to that one. That's it.
Correct. Exactly. Yeah, absolutely. In fact, so I will not have time to talk about this, but the WKB method of the first step in WKB analysis is the introducing the WKB ansatz, and basically my interpretation of that, my geometric interpretation of that, is that you have an upper with this filtration which is not flat, and you use it. You kind of use it as a leverage to construct the WKB filtration, and the way you do it is you interpret the WKB ansatz as a search for a splitting of this of the upper sequence, of an invariant splitting of the upper sequence. Yeah.
Thank you.
Yeah. Right. Okay. So basically, this is the outline of kind of everything I want to say, and the plan is to try to explain as much as possible of this. Okay, so first let me do something simple. So we're kind of in a local situation. I've trivialized everything. I've chosen a coordinate. So in other words, I'm looking at a differential system, a singularly perturbed linear differential system. So that's an object like this. Or to be even more concrete, I can input a vector field, and then this is literally a system of ordinary differential equations that looks like this, where A is for now an n by n matrix, which depends on X and on h bar, and I'll assume that it depends meromorphically on X, and that in h bar it's holomorphic at h bar equal to 0. But yeah, as I said, I've already mentioned it. There's this little asterisk here that actually it is even better to right away restrict your attention to much more general systems, which are not necessarily holomorphic at h bar equal to 0. You just need them to admit an asymptotic expansion in some sector as h bar goes to 0, with and then just impose some regularity on the kind of asymptotic expansion, or on the on the kind of asymptotics you allow. But anyway, I decided to take a simpler approach just for the sake of presentation. But maybe keep that in mind, that you can. And I mean, if you kind of look at the literature on singular perturbation theory, these are certainly the kind of systems that people like to study. They always have these matrices which are only defined in sectors. That's the usual setup. So so we can do the same. Oh yeah, and maybe I should like, as geometers, it's important to say that we can take the step forward and make that geometrically meaningful. And there is, and I already mentioned it, by using some kind of extension of scalars and using appropriate rings and so on. So, but anyway, for simplicity, let's just assume whatever, it's defined in some small disk, infinitesimal disk, etc. Okay, so what does it mean for a system to be filtered, right? So it's basically what I'm talking about here is a meromorphic H-bar connection on a trivial bundle, on the trivial bundle, right? I've trivialized the bundle, chosen a coordinate. So what does it mean for that trivial bundle to be filtered? So it means that I can put my connection into a triangular form. So there's some kind of gauge equivalence that puts my connection, my matrix A, into this upper triangular or lower triangular, depending on how you choose it, into this kind of form. So what is the filtration on the bundle in that sense? Well, the filtration then is just given by, basically just by the columns. Because I have this triangular structure, if I act on whatever the first canonical vector 1, 0, 0, 0, then my connection, because it's triangular, will send it back to some multiple of it, and so on. So this is the kind of structure these triangular systems have. And actually, if you think of these operations from a more practical point of view, which is, I have a differential system, I want to solve it. In order to solve it, I need to simplify it. So, the best way to simplify a system is to diagonalize it, because that once you've diagonalized it, it's done, you've solved it. But sometimes you can't diagonalize, and this will be the case here exactly. But it turns out that you can triangularize your system, put it into this triangular form, and that's almost as good, because it's just basically one step away from being able to solve the whole thing, because you basically then just solve it column by column. So it's a cascading coupled system. So the first equation is uncoupled, and you solve that, and then the solution of that couples into the second system. But now you've solved that, so it's just becomes like an inhomogeneous equation. So you solve that, and so on. So basically, having a triangular system is basically just as good as having a diagonal system. That's the message I want to, the practical message I want to make. Okay, so the point is that if I have my system nabla, and I can gauge transform it into a triangular system, the triangular system has this canonical standard filtration just by columns. And then I can use my gauge transformation to pull it back to my original system, and that gives me a filtration. Now, of course, there's a question of how invariant, like I use this gauge transformation to construct this filtration. How does the filtration depend on this gauge transformation? And that's what I mean by a filtration being canonical or not. So well, first of all, it should be, of course, independent of the coordinate x. Since this is geometry, we want things to be geometric in that sense. But also, you want it to be invariant or preserved by automorphisms of my original system. And again, there's an asterisk here, which is you need to be careful about what you mean by automorphisms. Which automorphisms are you talking about? So basically, you need to design appropriately your space of gauge equivalences. You don't want it to be too strict, because then you wouldn't be able to assign invariance to your connections objects. You also don't want it to be too broad, because then you would destroy all your invariants. All your connections would be equivalent. So you need it to be just right. The most kind of maybe your first guess would be, well, what if I mean, of course, I want holomorphic gauge transformations, holomorphic in X, holomorphic in H bar. Maybe I want them to be holomorphic at H bar equal to 0. So they're sort of holomorphic in this little disk around H bar equal to 0. It turns out the difficulty is that generically, so in almost all situations that you encounter, even when the system A here, the system that I started with, even if it's independent of H bar, so the only dependence on H bar is in front of the de Rham differential, even in those cases, generically, the gauge transformations that would take you to a triangular system are not holomorphic at H bar equal to 0. This is basically related to the very standard thing in singular perturbation theory, where you have one of these singular perturbed systems or equations, and you say, okay, right, I have this parameter H bar. Everything seems to look nice in the parameter H bar, so I'm just going to solve in power series in H bar. So I'm just going to plug in a power series in H bar and compute it term by term. And you can do that, and you can do that too here. But then you arrive at this power series, H bar power series solution, and its radius of convergence is 0. So clearly it's not an analytic object. You interpret it as an asymptotic expansion of an actual analytic object. And so this is exactly what we have here as well. So these gauge transformations that do allow me to simplify my system in this way, they're not holomorphic at H bar equals 0, but they are holomorphic in sectors at the origin, and they admit asymptotic expansions of certain regularity. So basically, the proposition for these singular Lipset systems, roughly stated, is the following. Again, at least in rank 2, there's a very large class of systems which can be filtered in a canonical way via gauge transformations, which are holomorphic in X and holomorphic in a sectorial domain in H bar, and they admit an asymptotic expansion in that sectorial domain, and that sectorial domain is a half plane, has the opening of a half plane. So basically, that's the statement. Okay, so let me. I'll basically I want to more or less give you the essence of the proof of this proposition, and in doing so, also make things more precise as I go along, and define what I mean by whatever large class of systems, etc. So, okay, so the first step is to go all the way to the singular fiber at H bar equal to 0, look at the algebraic object there, and diagonalize that. That's easy, and we're going to you just do that, and you kind of use that as leverage to continue in your quest for triangularizing the system for all H bar. So this is what I'll do. So from now on, I'll just restrict to rank 2, n equal to 2, and let me restrict X and H bar to some domain where my matrix A is actually holomorphic. So I'm thinking that the poles of my matrix A maybe are on the boundary of U. U doesn't even have to be a simply connected, so it could be, for instance, a punctured disk where at the origin of the punctured disk, my matrix A has a pole, something like that. So that's the kind of situation that I have in mind. All right, and then in the H bar, so I'm restricting myself to a little disk, and in fact, kind of the radial size of what's happening in the H bar direction never has absolutely any effect at all whatsoever, as long as it's non-zero. So as long as you can make things analytic. So I'll just restrict to, like, everything will be germ-like. So somehow everything I talk about in the X direction, it's function-like, and in the H bar direction, it's germ-like. Right, so to put it kind of completely precisely, on this U cross D, A is a 2x2 matrix with coefficients which are convergent power series in H bar with locally holomorphic coefficients. That's the meaning of this notation. Right, anyway, so there's a standard, very, very standard fact about holomorphic matrices. So if I look at the leading order, A naught, as long as I stay away from the zeros of its discriminant, then this matrix can be diagonalized by a holomorphic gauge transformation. So, but this only holds if I stay away from the zeros of the discriminant, which I call the turning point, which are called the turning points. So the first kind, or the zeroth kind of complete base assumption of about everything I'm going to say is that these open sets, these cells, or these open sets which are going to construct these cells that I mentioned before, where the WKB filtrations are going to be defined, they first and foremost, they shouldn't contain any turning points. And the other assumption is that on each of them, I want to be able to choose a univalued branch of the square root of the discriminant. So for instance, if U has no turning points and is simply connected, that is granted for free for you because it's a simply connected set. Of course, I can choose a square root discriminant, square root branch. But I'm also thinking of more general sets, maybe like an annulus or a punctured disk. So it's not simply connected. It doesn't contain any turning points, but I may be able to choose the square root branch of the discriminant, and that's enough for the construction. And this is not kind of a silly thing. It's actually important. I'll mention later about how to do WKB analysis for connections without poles, so on compact surfaces. And there, the situation is that these cells where I can construct the WKB filtration, they're basically annuli or cylinders.
Excuse me.
Yeah.
What is it is a discriminant of what? Of the minimal polynomial of the matrix? Or?
Of the characteristic polynomial. Yeah. So you
Okay.
take the, exactly, yeah, you take the matrix, take the characteristic polynomial, and take its discriminant. Yeah. Yeah, so these cylinders, sorry, these cells, they will be cylinders. So they're not simply connected, but I will be able to choose a square root branch of the discriminant on them, and therefore proceed with the construction and do WKB analysis on such domains. Okay, so right, so okay, so just to kind of be completely concrete, if I am in such a situation, so U has no turning points, I'm able to choose a square root branch. That means the two eigenvalues of my matrix A naught, they're distinct holomorphic functions, univalued, no branching. And there is a holomorphic gauge transformation P, which puts it into a diagonal form. And this matrix, this diagonal matrix lambda naught, of course, is unique up to permutation. Right, so that's what I say here, that this operation of taking my system and assigning this diagonal leading order part, this operation is canonical in the sense that it's not affected by coordinate change or automorphisms up to permutation. Right, so I've transformed the leading order of my connection, but now I can use the same gauge transformation. It's only x dependent, doesn't depend on h bar. So I just transform my connection, my system nabla by it, and I get a new system, which has a kind of still complicated form, but simpler and a more useful form. So I've pushed all the complexity out from the leading order in h bar into the subleading orders. So there's this h bar in front here, So all the non-diagonal or non-triangular aspect of my connection is now in h-bar subleading order terms. And so now this is the connection that I want to put into a triangular form. And so that's step 2. And that's what I call, it's a kind of, you could say maybe a generalization of what you would call a WKB ansatz, or maybe it's related to the WKB ansatz. So yeah, so basically, so the idea is that I'm going to put my system nabla prime into a triangular form by searching for a gauge transformation in a special form, which is this unipotent lower triangular form. So here S is some function that I need to determine. So I need to write down an equation for this function S such that G transforms nabla prime into something triangular. So if you do this calculation, you get the following. So this isn't actually very, it looks maybe a little bit messy and complicated, but it's not really. What's going on here is the following. So I take my system nabla prime and I gauge transform it, and the matrix of the system looks like this. So the 3 terms, so these 3 terms, they're not really important. They're just, something that you get from computation. What is really important is this lower left corner, which I separated into star because it's the longest. It basically looks, well, it has this expression. So this term, this derivative term, comes from the gauge term, the G dg inverse. This term comes from conjugating the leading order diagonal matrix, and then the rest, comes from conjugating the matrix B. And that's why there's the overall h bar everywhere in front. Okay, let me remove all this. So now the point is that I want this gauge transformation G to simplify my system nabla prime in such a way that the resulting system is upper triangular, which means I want this lower triangular star term to vanish. So the condition is that my system is filtered, or nabla prime is triangular, nabla tilde is triangular, if and only if this test function S satisfies what you can clearly see is a Riccati equation. It's a first order differential equation, which is quadratic in S. Here's the nonlinear term. A2 and A1 and A0 are whatever, they're just these coefficients. I made it simpler. The square root discriminant here, I've replaced, I've chosen the square root in such a way that this difference of eigenvalues lambda 1 minus lambda 2 is that square root. And then, of course, very importantly, this is a singularly perturbed system because the derivative is multiplied by my parameter h bar. And so, right, so somehow I've reduced my problem of, putting my connection, putting my system nabla into a triangular form to solving this first order nonlinear differential equation. Oops. Right. So how, okay, so how do I see the filtration? So, suppose I did get a function S which solves this Riccati equation. Then this standard filtration on on the triangular system nabla tilde. So this is for nabla tilde. That I need to pull it back using my gauge transformations to my original system nabla. So that means I need to apply the 2 gauge transformations that I've used, P and G, and go back. And so G being this very simple lower triangular form, I've already multiply G inverse by 1, 0, by the vector 1, 0. The reason I did that is I want to kind of make a note that if I do manage to find such a gauge transformation G, this of course gives me a filtration. I just constructed it for you. But then there is a question of canonicity. How does this filtration behave under automorphisms of my original system? You can see that because I've written my filtration in this special form, where I have basically the fact that this entry is 1 is kind of an important thing. Well, the short thing to say is that if the canonicity of this filtration basically boils down to being able to canonically pin down this gauge transformation G, because if my gauge transformation G is if I solve my singularly perturbed Riccati equation, I get 2 distinct solutions which equally well satisfy the Riccati equation and therefore equally well give me a filtration. Those 2 filtrations, they would be generated basically by something like 1 minus S or 1 minus S prime. And because S and S prime are different functions, these filtrations are going to be genuinely different. And that difference, you would not be able to absorb it into P. So anyway, this is a very long way of saying that. Sorry, I skipped one point. So the point I'm talking about right now is this. No, not even this. Sorry, this. I skipped 2 points. So yeah, the point I'm talking about, the point I'm saying is that the ability of me to construct this filtration in a canonical way rests upon the fact of being able to construct a canonical solution to the Riccati equation. And canonicity in this sense usually means uniqueness in some form. If I can nail down a unique solution satisfying some natural conditions, then I'm guaranteed that the gauge transformation that I produce is canonical, canonically chosen, and therefore the filtration that I construct is canonical. So anyway, that's the message I'm trying to convey. Okay, so there's 2 more points that I inadvertently skipped. One, which is we do want to preserve asymptotics or have asymptotic control as h bar goes to 0. And you can see that because of the form of G being this lower triangular form, G admits asymptotics even only if S, the solution to the Riccati equation, admits asymptotics. So we really need to search for solutions of the Riccati equation which are exact, meaning that they're holomorphic solutions in both X and H bar and have good asymptotics. They admit asymptotic expansions. And furthermore, by looking at this equation, you can see that the leading order term of if such a solution exists, so that it has an asymptotic expansion, the leading order term of that asymptotic expansion has to be 0, simply because if I look at the leading order term of this Riccati equation, so if I basically literally just set h bar equal to 0, all I get is just this this term equal to 0. But because we're assuming there are no turning points, that means the discriminant is non-vanishing, and in particular the square root discriminant is non-vanishing. The only way this product can be 0 is if the leading order term of S is 0. So basically, just by kind of examining your setup, you see that you have these 2 conditions staring you in the face. And so now going back to this idea of canonicity and being able to nail down my solution S uniquely, these 2 facts that I mentioned, there you could literally interpret them as a kind of asymptotic initial value condition for my Riccati equation, and that's with appropriate assumptions that gives you a existence and uniqueness of solutions. So yeah, right. So how do you do this? So I keep emphasizing that the uniqueness, the existence, of course, is very important. Otherwise, we wouldn't be here at all. But the uniqueness part is also crucially vital, because without uniqueness, I'm not able to make geometric statements, kind of canonical invariant statements. So, okay, so I'm looking, so somehow everything rests on this singularly perturbed Riccati equation. And basically the upshot is that this equation has a canonical exact solution, meaning that it's defined and holomorphic in X and H bar, and it's defined for H bar in a sectorial half-plane germ domain, provided two important assumptions. One of them is on the kind of geometric shape of U. It has to be complete under a flow of a certain vector field, and number two is that my equation needs to have some regularity with respect to this flow. So as I flow my system in the limit of that flow, I need some boundedness. So okay, so let me walk you through that. So the vector field in question is this one. It's just 1 over square root discriminant times d by dx, and you can see just by looking at the Riccati equation, you can see why this vector field could be important. It's because the discriminant of the leading order part of this equation is delta naught. If I divide both sides of this equation by square root discriminant, so if I put the square root discriminant, that will disappear, and then I just have this. Then now the discriminant of this, the leading order part of this equation, is 1. So somehow it's almost like a normal form reduction of my equation, and I do this reduction at the expense of replacing this simple looking differential operator d by dx by this more complicated holomorphic or locally holomorphic vector field. So anyway, so that's the vector field I need to consider, and I need to consider the flows of this vector field. More specifically, I want the kind of real flows in a certain direction. By that I mean you take this holomorphic vector field, you take its real part, that's now some kind of real analytic vector field, and so I can consider its flows, and I will flow it in one direction. So because right, so yeah, as I said, in positive time, this is a real vector field. There's a notion of positive and negative flow time. So concretely, if I actually want to kind of write down a formula for a flow line through a point, then it's given by the vanishing of the imaginary part of this integral. And no doubt this kind of expression will be familiar to many people in the audience. This is exactly the sort of things you see in exact WKB literature. Okay, so then the two assumptions, I've already kind of mentioned them, is that my open set U is if I take every point in open set U and flow it using this vector field in a forward direction, then the flow is complete, meaning that it exists for all positive time. So I can flow for infinite time forward. And the second assumption is that as I flow my system, my coefficients should be bounded by the square root discriminant kind of in the limit of my flow. So at the end, there needs to be some kind of boundedness. So with these assumptions, the statement is that the Riccati equation here, which is here at the top, has a unique holomorphic solution on this U cross sector S. And the uniqueness is given by the fact that it admits an asymptotic expansion as h bar goes to 0. And the asymptotic expansion is of class Gevrey, if you're not familiar with that, it doesn't really matter. It's some regularity on how coefficients in the asymptotic expansion grow, and it's valid uniformly in the entire closed half-plane sector, and its leading order term is vanishing. So you get this nice existence uniqueness theorem. Right. Okay. So, and then as conclusions, then somehow this is at least on the local level the main theorem, which is so if I use all these assumptions 0, 1, and 2 to remind you what they were. 0 was about the fact that I have no turning points and the fact that I can always choose this square root branch of the discriminant, and that I want my open set U to be complete under this vector field flow. And that in the limit of the vector field flow, I want those coefficients of the Riccati equations, which are ultimately entries of my matrix A, I want those to be bounded by the square root discriminant. Then I get the following conclusions. So 1, if I take my system and I restrict it to this domain U cross this sectorial germ, that has a canonical filtration. And this filtration has the property that if I take its associated graded, now that's some kind of diagonal system, that is an Eigen decomposition that converges to the Eigen decomposition of the leading order term as h bar goes to 0. Number 2, if my flow domain U flows into a pole of my system, then for every fixed h bar, I have a genuine meromorphic connection, not an h bar connection. And as long as that non-zero h bar stays kind of close to the real positive direction or is on the real positive direction, then the local WKB, this local WKB filtration for this fixed value of h bar coincides with the corresponding Levelt filtration associated with the pole P, or with the Stokes sector at this pole P. The staying close to the positive real direction is kind of important because the Levelt filtration basically depends on the, let's say if P is a simple pole, then it basically depends on the eigenvalues of the real parts of the eigenvalues of the residue. And in this case, they are going to be eigenvalues of the residue divided by h bar. And so the Levelt filtration depends on the kind of interplay of which real part is more positive and which real part is more negative. And as you change the angle of h bar, then that interplay might get ruined. So, but as long as you kind of there's always the small, might be very small kind of interval of directions such that the Levelt filtration interplay of real parts remains unchanged and coincides right, and gives you a filtration which coincides with the WKB filtration. So somehow everything is matching. Okay, and then number 3, which is a kind of final step, which is that so you do get these. If you are in a situation where your flow domain is actually complete by flowing it in both directions, so you can flow it forward or you can flow it backward, then by flowing it forward, I can construct my WKB filtration in the way that I just explained. But then by flowing it backward, you can do the same thing, just basically by permuting and doing a similar analysis, and you construct another WKB filtration. And those WKB filtrations are different. Basically by comparing maybe the explicit formulas for this S in the gauge transformation, you see that they genuinely have to be transverse. They are transverse filtrations. So you intersect them, and therefore you get a decomposition, a kind of WKB basis for your system, a local WKB basis, local exact WKB basis for your system. Right. Okay, so I have maybe like a minute or two left. So right, so that was the punchline, that you get a canonical diagonalization over this U cross S. So let me just finish with just 3 remarks regarding the exact Riccati, exact solutions of the Riccati equation. So I've already mentioned several times that, you know, I'm assuming that everything is, you know, my systems are holomorphic and it's some kind of small disk around h bar equal to 0, but I don't have to. And in fact, the proof is not much more difficult if I right away restrict to a sector of you know, specified opening, and then I just assume that my coefficients, they're not holomorphic at h bar equal to 0, but they have asymptotic expansions of a certain regularity, and then you get a very similar exact existence and uniqueness theorem for solutions of the Riccati equation. Right, so in that case, what you do is you look at the leading order equation, a leading order part of this equation, which is some kind of quadratic equation, and, you know, generically has 2 distinct solutions, and therefore generically there are 2 distinct exact solutions to the Riccati equation. Again, provided all these flow and regularity conditions are satisfied in any appropriate way. So, and I should say, of course, somehow this very technical result of being able to get exact existence uniqueness of solutions for the Riccati equation is at the heart of the construction. That's the technical heart of the construction. The proof is inspired by ideas of Koike-Shafke about Borel summability of WKB solutions. Right. So the second remark, which is it's a consequence of this, which is that so I actually get these local WKB filtrations and therefore global piecewise WKB filtrations for a much larger class of systems, which are defined in these sectors to begin with. Again, you just need to restrict asymptotic regularity involved. And then last, probably very important point is that this existence uniqueness of exact solutions for the Riccati equation implies a kind of a very general existence uniqueness theorem for exact WKB solutions for the Schrodinger equation, and the Borel summability of the formal WKB solutions of the Schrodinger equation. But not just the Schrodinger equation, actually much more general things. So, you know, on the one hand, you could say that I'm able to cover all second order ODEs, so not just in the Schrodinger form, and moreover, the coefficients may be, you know, really quite general. They don't have to be constant or well behaved at h bar equal to 0, apart from the fact that I want them to admit an asymptotic expansion of some reasonable regularity. But then, of course, you could take it further and say, because I have the uniqueness of solutions, and therefore, and I'm able to translate it into some kind of canonicity of the construction, I'm able to geometrize this and say it's not. I'm able to do this for general rank 2 order 2 scalar differential operators on an arbitrary line bundle. It doesn't have to be the trivial bundle. It doesn't have to be the anti-canonical line bundle. It can be any line bundle on a compact Riemann surface, and I can set up this problem. I can look at the singularly perturbed second order differential operator, and I can construct exact WKB solutions to it in specified domains. Okay, so I think maybe I should, I think I've run out of time, so I should stop here.
Okay, thank you very much. Maybe we can thank the speaker for the talk. And so are there any questions? maybe I can start with one question about. So you get Gevrey asymptotics on some special half plane, and I would like to know if you have some kind of summability, meaning that you can cover by half planes and have Gevrey asymptotic on each.
Yeah, it's so far I've not gone into kind of analyzing what happens as you start rotating the phase. That's the very natural next step indeed. But indeed you I mean basically the way the way the solutions of this are constructed is Borel-Laplace method. And so you get the solution, which is like a Gevrey germ in a half plane. And then so the thing that I mentioned about when I was talking about the coincidence of the WKB filtrations with the Levelt filtrations, that somehow you want H bar to be in this, close to the positive real direction, but it can be in some small opening. That's somehow related very much to the gluing that you're mentioning, because essentially the reason why you need to stay close to the positive real line is really the bisector of this half plane. So along the bisector, the geometry of all these flow domains is set up exactly the way I need it. If I rotate H bar a little bit, then the geometry changes, but in a kind of isotopic, in an isotopic sense. So although the setup is different, it's in some way equivalent, and therefore you can perform the same analysis. And then there's basically just a Cauchy-Goussat argument that you can glue the constructions as you rotate the phase of H bar. But then there are these critical kind of directions in the H bar plane where the geometry of these flow domains changes, and then those are from the point of view of kind of resummability, those are the bad rays, that somehow something bad happens and you no longer can get a unique exact solution. But
these bad rays depend on what?
Yeah, so
on the shape of the equation.
So I basically the one thing that I didn't introduce, or I introduced and implicitly assumed it to be zero, is the argument of H bar. So basically you start with a system and it has H bar and it has several parameters, and before I proceed with any of the constructions, I need to decide which phase I need to pick, and I sort of implicitly chose that to be the positive real direction. Of course, if you're just interested in a single phase, then any phase can be brought to be the zero phase just by rotation. So somehow, if you're not interested in rotating, you don't have to mention the phase at all. But once you do want to get this kind of family gluing, then you need to worry about the phase. So in that case, the foliation that comes from, like the vector field that I would be flowing would be not L, but L multiplied by like e to the minus I theta or something like that. So I would rotate that vector field.
So yes, so if you consider your complex vector field, which is defined by 1/square root of delta naught, then you can multiply this vector field by a complex scalar, and you have another flow which is rotate, which has
exactly.
This is what you mean.
This is exactly what I mean. Yeah, this is exactly what I mean. Yeah.
And for some direction, it can be not. You can not have the assumption.
That's right. I mean, the typical thing is that if you're sitting at a point and flowing it and start rotating the flow, eventually it'll hit a turning point, and then you're kind of stuck because assumption one is not satisfied because that flow is not complete. You run out of time in finite time.
Okay. Thank you. Yeah. Is there any question now? Jens?
So may I have a question? Hello, yes. Nikita. So
hi.
Hi, can you say something about assumption 2 as well? So in practice, how can you check that assumption 2 holds without, you know, computing A0, A1, A2?
Yeah,
Is there any method to
it's
check
actually,
it?
yeah, it's actually, I agree. This assumption looks much scarier than it actually is. So if you really are working with a meromorphic connection, you look at the pole. Sorry, if you really are working with an H-bar, meromorphic H-bar connection, so there is a parameter H-bar. So you look at the principal part of your connection at the pole, right? So it's some polynomial in whatever 1 over x, etc. But also depends on H-bar. Sorry, it's a matrix whose eigenvalues are polynomials in 1 over x. So now the condition is right, and then and the limit of that as h bar goes to 0 is just the kind of leading order part of that polynomial. Sorry, the leading order. It's still a polynomial in 1 over in powers of 1 over x, but it has no more h bar. So basically, what you the second object is the principal part of the Higgs field at the pole. Higgs field is the leading part. So the condition is very simple. You want the eigenvalue of the Higgs field to be sorry, you want the principal part of the eigenvalues of the principal part of the connection to be no more singular than the eigenvalue of the Higgs field. So basically, you just take the eigenvalue of principal part, you divide it by the eigenvalue of the Higgs field, and if that vanishes as or if that has a limit as x goes to 0 to the pole, then you're good. Basically, this is heuristically what this means is that I want the polar behavior of my connection to be contained in the leading order part, in the Higgs field. So the H-bar sub-leading order part of the connection may still have poles, but they're dominated by the poles in the leading order.
I see. Okay, thanks.
So from a practical point of view, it's very simple. Yeah. At least in the case of poles, because then you can really do what I said, like divide polynomials one by another.
I see. Yeah, and there's no way to make the filtration work wherever the discriminant vanishes. Is that correct?
Yeah, that's right. So where the discriminant vanishes, those are the turning points, and that's where the filtration really, it just goes berserk. Yeah, I don't think. I'm not sure if there's a clever way of constructing something over the discriminant locus that maybe some kind of twisted filtration. I'm not sure. I mean, I'm thinking about this on and off. But also maybe it's not very crucial. Yeah.
Okay, thanks.
Yeah. But actually, the other thing that I would like to say, maybe kind of capitalizing on that question since you asked, is that so these filtrations, they are defined over these cells, and these cells have overlaps, and over the overlaps, they're kind of like strips, kind of like horizontal strips, and over each of these you get a pair of transverse filtrations which you intersect to split your bundle. So then you could say, okay, well, I don't just have a piecewise filtration, I have a piecewise decomposition of my bundle. Great. So that piecewise decomposition is now defined away not just from the discriminant locus, the turning points, but actually away from a graph, a real codimension 1 graph, the Stokes graph or the spectral network, lots of words for this. And so then the interesting thing is this. So on the complement of the Stokes graph, you get these canonical decompositions. But above a Stokes edge, which is adjacent to 2 strips, you don't get a decomposition. You get a filtration. However, you can take that filtration, you can still take its associated graded, and you get some kind of split bundle. That split bundle is not your original bundle. It's an associated graded. But there are two isomorphisms between your original bundle and this associated graded. And they're given by the fact that this edge is adjacent to two strips where I do get genuine decompositions. So I get two isomorphisms which compare or which there are isomorphisms between the associated graded and my original bundle. And the key point is that those two isomorphisms, they don't agree. They're different isomorphisms. They're kind of like they're basically related by like a shear transformation, like a unipotent upper or lower triangular shear transformation. And those right, okay, well now I'm getting like way off into another topic, but basically these disagreements of these identifications between the associated graded and the original bundle, you can encode them into a cocycle, which I call the Vorosco cycle. And this Vorosco cycle is responsible for another construction, which is called the abelianization. So you take your rank 2 connection and you abelianize it to a rank 1 connection on a double cover. So somehow I never mentioned any double covers in my story because I didn't want to go in that direction. But basically, this square root discriminant, square root delta naught, is nothing but the canonical one form on the spectral curve. That's all it is. And delta naught is a quadratic differential defining the spectral curve. Or it's related. Yeah, it's a bit different. But anyway, so so on this spectral curve, you can use these pieces of WKB filtration, or the pieces of the associated graded of it. You can put them on the spectral curve, and there's a natural way to glue them into a single line bundle with, so it's a line bundle with H-bar connection. And then to recover your original bundle, basically you push it forward, and that recovers for you the kind of more or less the diagonal part of your original connection. The information that you haven't included is the off-diagonal data, and that is the Vorosco cycle. And then okay, so sorry, I'm just too excited about this, I think. So and then
another talk.
yeah, right. But then the most remarkable thing, and that's basically the observation of Gaiotto, Moore, and Knightsky, and that is that this Vorosco cycle, although it sounds like you need to have both the line bundle and the original vector bundle in order to, it seems like it's a lot of data. It's the off-diagonal part. But their great discovery was to recognize that because my curve is split in this very simple combinatorial way, the information in that cocycle is obtained in a very standard way from my abelian connection on the spectral curve. Is basically you take your connection and always integrate it, take parallel transport along some simple canonical paths, and whatever connection you pick, whatever connection you feed it, it's always the same operation. So it's actually no more information than the original line bundle itself. So it's a really combinatorial object. There's no continuous parameters in it. Is what I'm trying to say. Okay.
Thank you. So thank you again for your talk and long explanations.
Thank you.
So I don't know what is the next talk. It is already scheduled. Masaiko.
Oka-san, what was the next plan?
So the next plan is Hiroe-san on 28 April.
28.
28. Now we have Hiroe.
Yeah.
From Chiba University, I think.
Yeah, from Chiba University.
Yeah.
Okay. So thank you again.
Thank you so much.
Thank you, Nikita. Yeah.
Yes.
Thank you.
And so
Goodbye.
So goodbye. Bye.
Bye. Bye. Bye.
Bye.
See you. Bye.
Thank you very much.